Hi everybody. In this video I'm going to talk about one of the three classes of sedimentary structure that we identified and talked about earlier. I'm going to talk about primary depositional structures. And by far the most important and dominant primary sedimentary structure that occurs in nature is stratification. Stratification is the layering of sediment in a sedimentary deposit. And before we talk about the different types of stratification that can occur, it's important to talk about what actually causes stratification. So if you look at the layered deposit on the left-hand side of the screen here, the layers that you see in here are caused by one of 5 different types of variation in the way that sediment has been deposited. The first and probably the most obvious of these 5 things is that the composition of the sediment could have changed from layer to layer, and I think you see that right here. This is all sand in this area, and then there's this little gap which I believe is probably a mud deposit, a more clay deposit, and then it goes back to sand again, and so the occurrence of that mud layer in there defines a lamination that's based on composition. Other things that can vary could include the size of sediment. You can have, say, coarse sand and coarse sand that define a layering in a deposit, and then you would see bedding planes right along the boundaries between those layers. The shape of grains could change. You could have flat lying grains and then spherical grains and flat grains again. The orientation could change. You could have grains deposited flat and then grains deposited at an angle, and that could define some type of layering in the rock. And then finally, another common occurrence is packing. The way that sediment is packed together when it's deposited can define bedding planes and layers as well. So here we've got a tightly packed layer, and sandwiched in between them is a loosely packed layer. And all 5 of these things are caused by changes in the way that sediment is being deposited over time, which together gives you this record of change in time over a particular time interval. Okay, the surfaces that define the boundaries of strata or beds are called bedding planes. Bedding planes can also be called contacts. They're the point of contact or the plane of contact between one bed and another. Bedding planes are surfaces that define the stratification in the sediment and represent the sediment surface at the time of deposition. I just want to reiterate this. They are basically representing the surface of the earth at the time the sediment was being deposited. These surfaces, these bedding planes, may either be erosional surfaces or depositional surfaces. So if you look at this image up here at the top, what we have is we've got a series of layers, some of which are depositional surfaces and some of which are erosional surfaces. You can pick out the erosional surfaces because they cut through the depositional surfaces. The beds in this case down here are truncated by this erosional surface number 1. The beds here onlap that surface, are basically draped over this erosional surface, and then they are truncated by erosional surface 2, and then more depositional surfaces are deposited on top of that erosional surface 2, and they onlap it. Changes in sediment character that define the bedding may be gradational, very gradual, or they could be sharp. And so on this image here on the left, we've got a very sharp contact here, where the character of sediment changes very abruptly. And then we've got a gradational contact here where the character of sediment changes over a broad interval. Generally, sharp contacts mean abrupt changes, and gradational contacts mean gradual changes. Okay, bedding planes, these surfaces, bound beds or strata. And the orientation of the bedding planes with respect to the ones above and below them define the shape of the bed. So bedding planes can either be parallel or non-parallel, and they can have a variety of different types of character. Parallel bedding, bedding where each layer is parallel to the one above and below it, produces tabular beds, large sheet-shaped volumes of sediment that are all parallel to each other. So here's a good example of some tabular beds in Canyonlands National Park. Non-parallel bedding planes bound discontinuous lens-shaped packages of sediment, which we call lenticular beds. So down here we've got a picture of a single bed of sandstone that is thick on the right-hand side of the image and then pinches out to nothing on the left-hand side of the image. And in 3 dimensions, this would have the appearance of a lens-shaped package of sediment. I've already used the term laminations in the prior video, and the term lamination refers to a very, very thin bed. So in this image, there's a fingertip for scale. Lamina are beds that are less than 1 millimeter thick, approximately. So all of these individual layers of sand, we would refer to them as laminations. If the lamina are tilted with respect to horizontal, we would call them cross lamina. Lamina can be bundled together as part of a bigger unit that we would call a bed. And beds can have a variety of different thicknesses, and this is just a general way to characterize what we mean when we say very thick bed, very thin bed, medium bed, etc. Both beds and lamina can be bundled together into bed sets or lamina sets. So I'll talk about beds and bed sets here. A bed set is a package of beds, often that is repeated over and over and over again, some package that has an arrangement that is characteristic of the sedimentary deposit as a whole. So to give you a couple of examples here, we can have either simple bed sets in which all the sediment is the same thing, here all sand, or we can have composite bed sets where you have 2 different types of sediment, here sand and mud. The bed sets that are shown here are packages of sediment that start off with thick beds, and as you go upwards, they get thinner, and then they get thick again. And this package of upward thinning simple bed sets, this is one simple bed set, may be repeated over and over and over again. So you could have another package just like this up here and another package just like this down below. And it's pretty obvious usually when you have bed sets what constitutes a bed set. It's just a repeated package of beds, all of which has the same character. So on the right here, we've got a bed set starting here and ending here. This would be an upward thinning composite bed set. Sand, mud, sand, mud, sand, mud, sand, mud, and the sandstone gets thinner and thinner and thinner as you go up. You'll notice that the same sort of thing is repeated, although not as clearly down here, and then there's another thick bed up here that does the same thing. Okay, another thing that you commonly find with stratification in a sedimentary deposit is that it's not all horizontal. You often have cross-stratification. We've talked about cross-stratification already. Cross-stratification is the product of migrating bedforms on the sediment surface. And by bedforms, I mean things like ripples or dunes. So if you look at what those might look like on the sediment surface, you can actually have two main classes of bedforms. Two-dimensional bedforms, 2D bedforms, are bedforms in which the third dimension doesn't really matter. You would call these straight-crested dunes because the crest of the dunes is straight. There's no curvature to it at all. And what that produces is it produces cross-stratification that can only be seen if you are looking perpendicular to the current direction. If you look upstream at these, you just see horizontal bedding because there is no curvature to the cross beds or the surface on which the sediment's being deposited, the downstream side of these dunes. 3D bedforms are bedforms that do have curvature. So these are a type of dune called a lunate dune, where sediment is deposited in a scoop-shaped depression on the upstream side, and all the sediment is deposited on this surface, and then downstream of that surface you erode out a little pit. And so what happens as the current pushes these bedforms in this direction, as they migrate that way, the sediment that is being deposited on this downstream side of the dune ends up filling up this erosional pit, and you basically dig a scour that migrates in the direction of current, and then the cross beds migrate over the top of it. And what that produces is a pattern like what's shown here, where if you look upstream, you see these little pits that have been eroded into the underlying sediment, and the cross beds that fill those pits are curved. So you see little smiles. If you look perpendicular to the current direction, you basically just see cross beds more or less of the same character that you'd see over here with migrating 2D bedforms. So let's take a look at what these things look like in outcrop. Here is an outcrop of tabular cross-stratification. You see a horizontal surface here, a horizontal surface right here, and in between those surfaces we see crossbeds. And you see the same thing repeated over and over and over again. Here's another great tabular bed down here. So the beds are tabular, and the crossbeds are just embedded within that tabular bed. Trough cross-stratification looks quite a bit different. So this is a photo of large-scale trough cross-stratification. And what you'll see here is that there are several surfaces, these scoop-shaped surfaces, that are erosional in nature. And those scoop-shaped surfaces that truncate the underlying beds are filled in from above with crossbeds. Here's another surface that truncates the beds below it, and it's filled in from above with more crossbeds. So this is an example of trough cross-stratification. Pretty complex geometry. Let's look at trough cross-stratification in a little bit more detail now, and I'm going to show you an outcrop here that in one view we are looking upcurrent. So what you can see here is you can see a trough that cuts down into the beds below it, and that's filled in with these sort of smile-shaped cross beds. That trough actually kind of goes up sort of like that. And then down below we see some pretty confusing array of cross beds. that almost look like they're going two different directions. And that's simply because we're looking at different sides of troughs. Here we're looking at the right-hand side of a smile. Here we're looking at the left-hand side of a smile. And so it can be pretty confusing to observe troughs when you're looking at some angle to the current direction. But if you were to go over to this side, the left-hand side of this same block, and look at this face, you'd see something quite different. Now we're looking at a side view of the same outcrop. So before we were looking at this face here on the right, and what you see here are cross beds that are all going in the same direction. They're all headed off to the right. And these are the cross beds that are filling those troughs. And it's just simply because we've changed our orientation that they appear to all be going the same direction. If we were to then walk to the top of this outcrop, stand on top of this and look down, we would see something different. Here what you're seeing is you're seeing the edges of one of those troughs. So this is the scour, and it's filled in with the scoop-shaped surface upon which sediment is being deposited. So these are the actual downstream sides of those migrating dunes, and that's telling you that the current direction is going that way. Okay, so let's put all this together for a good descriptive set of terminology for describing crossbeds. We've talked about trough cross-stratification and tabular cross-stratification, but we haven't talked about yet is the orientation of the foresets, or the geometry of the foresets that fill in these curved surfaces that define troughs, or the planar surfaces that define tabular cross-stratification. So in general, there can be three different types of foreset or crossbed geometry. Planar crossbeds, or planar foresets, are simply just straight lines from top to bottom. Tangential foresets are curved. They start off steep and then they merge to become parallel with the underlying surface. And if that surface itself is curved, then you still get tangential foresets, but they merge in with the curved surface below them at a slightly different angle, depending on the orientation of that curved surface. Sigmoidal cross-stratification basically curve into the lower bounding surface and then flatten out towards the top, and this is the type of thing that you would see if you were preserving the top of a dune as well as the bottom of a dune. One thing to note about this is that tangential foresets are always concave upwards. They curve like this, not like that. And this provides good facing direction for the beds that they're in. They're a good way up indicator, so you know that if you see curvature like this, that was the up direction. If you were to instead see a curvature like that, then you would know that the beds were upside down. So let me give you an example of what that might look like in an outcrop. Here's a question for you. Which way is up in this outcrop? This is a photograph I took of some beds in China in a region where the rocks are so deformed that they are very commonly upside down. And what you see here is you see a curved surface that truncates the stratification below it, and that curved surface is concave in that direction, telling you that B is the way up in this particular example, and there are cross-stratification, layers of cross-strata above this curved surface, actually below it now, but they were above it, that are curved as well. And so that curvature there tells you which way is up. You can see curvature even in this bed here. In addition to the geometry of foresets, we also need to consider whether the bedforms are migrating under conditions of sediment transport or under conditions of sediment transport and deposition. And so I'm going to show you two examples of what can happen when ripples migrate downstream. The first at the top here is what might happen when ripples migrate under steady, uniform flow with no new addition of sediment to the bed. So the sediment's just being transported along the bed. Ripples will just simply transport until the current stops, and then they get buried. So let's watch what that looks like. Ripples migrate down current. There's no new addition of sediment to the bed, so when the current stops, the ripple drift ceases. And then deposition, from whatever happens next, buries those ripples, and you get what's called starved ripple cross-lamination. And as an example of that, the outcrop I showed you in the last video had a great example of starved ripple cross-lamination. Okay, we'll contrast that with what might happen when ripples migrate under conditions of depletive flow. In other words, where flow is spreading out. In that particular case, sediment that could be held in suspension upstream will rain out when the flow spreads out. And when you get sediment raining out from suspension, that adds sediment to the bed, and the bed degrades, or it grows in height due to that deposition. And so what you get is you get sort of a contest between the rate at which the bed forms migrate downstream and the rate at which the bed grows in height. So let's watch what that looks like. So here we've got a low rate of bed aggradation and a fast rate of ripple migration, and you end up getting cross beds that climb. As you increase the rate of bed aggradation, you increase that angle of climb. So if the bed aggradation starts to compete strongly with the rate of ripple migration, you can get a very steep angle of climb, and we call these climbing ripples. This is a good outcrop example of climbing ripples. So what we see here is we see ripples where the upstream side and the downstream side are both preserved. And that angle of climb is basically something like that. So when you get non-uniform flow, in other words, where you get flow that's spreading out, if you have steady flow, the current is always steady and steadily producing ripples, but you're adding sand or sediment to the bed from suspension because the flow is spreading out, then you end up getting climbing ripples. And again, we can see that angle of climb right through like this. I'll draw that in for you. And the angle of climb is related to the rate at which the bed grows in height versus the rate at which the ripples migrate downstream. So this is a typical feature of non-uniform flow where the flow is depletive, it's spreading out, and as a result of spreading out, you rain sediment out from suspension on the bed below. Now let's look over here at the case of unsteady flow. Here is a situation where you have rippled sand interbedded with mud, and what that represents is a change from a slow current producing rippled sand to no current producing a deposit of mud. Down the bottom you have what's called lenticular bedding, where you just have single ripples preserved and encased in mostly mud. This would be a situation where you have only short periods of time where you get a weak current and the rest of the time you have no current. When you have a stronger current for longer, you end up creating more and more sand beds and less mud. This is called wavy bedding. And then finally you can have a situation where most of the time you've got a current. It may switch directions, and most of the time that current is producing ripples, but then every once in a while you stop that current and you drape those ripples with mud, but by and large most of the deposit's sand, and that's called flosser bedding. This type of bedding, flosser, wavy, and lenticular bedding, is usually associated with tides, because tides come in and they produce a current as they do so, and then during high tide they just sit there, no current. And then as the tide goes out, it produces a current in the opposite direction, and then during low tide you get still water again. And that is a perfect mechanism for producing an arrangement of bed forms that looks like this. Okay, quiz time. What was the current direction here? Well, one of the things that your eye will typically be drawn to are these surfaces, which, if you're not looking carefully, could be thought of as crossbeds. But in fact, what you're really looking at there is the angle of climb on climbing ripples. And what gives it away is that the actual crossbeds are here, in between those layers. And so this is an example of climbing ripples where the angle of climb is pretty steep and the current direction is A, off to the left. So the current was going that way. Okay. Ripple marks are features that you can find on the surface of a bed that preserves the form of the original ripples. And they're pretty common in a lot of different environments. And there are generally two different types of ripples that can form in two different types under two different types of currents. Wave ripples are produced by oscillatory flow. In other words, as a wave goes over the sediment surface, it goes one way and then it goes the next way and it keeps oscillating back and forth. This would be the type of ripples that you find offshore of a beach or something like that. In a river, you have a unidirectional flow. The current's only going one way, and that produces a slightly different type of ripple. And you can measure, there are two measurements that you can make on the form of ripples that'll sort of help guide your decision as to whether the ripples you're looking at were produced under oscillatory currents or unidirectional currents. And the general idea is that oscillatory flow produces ripples that are of short wavelength relative to height, and they're symmetrical. So the upstream side and the downstream side have the same length because there is no real upstream or downstream side. Current ripples, those that are produced under unidirectional flow, typically have a large upstream side and a very short downstream side, so they're very asymmetrical. And they're also usually a lot less high relative to their width. And so the ripple index is a measure of length versus height, the width of the ripple versus how high it is. And wave ripples produced under oscillatory flow have very low ripple indexes because they're pretty high relative to their width. And current ripples tend to have a very large ripple index because they're not very high with respect to their width. The ripple symmetry index is another measure to differentiate wave ripples from current ripples. Wave ripples, those produced under oscillatory current, are very symmetrical, and current ripples produced under unidirectional flow are very asymmetrical. And so the ripple symmetry index is a ratio between the upstream side, the length of the upstream side of the ripple, versus the length of the downstream side of the ripple, LS and LL. And so the larger that is, the more likely it is that your ripple was produced under unidirectional flow. So if you look at this example here, we have a set of ripples that have a pretty long upstream side and a pretty short downstream side, and they're also not very high. These are current ripples, pretty much similar to these, produced under oscillatory flow. on this image here, we've got a set of ripples that have crests that are pretty close to each other and pretty symmetrical. Those are the troughs. So the upstream side, one side of the ripple is about the same length as the other side, so they're pretty symmetrical, and they're also much higher than the ripples you see over here, and you can see how high they are by looking at that surface there. And so these are wave ripples produced under oscillatory flow, different forms of ripples. Ripple marks can also have a set of different set of geometries. They can, just like any other bed form, be straight crested or two-dimensional. And as you get into faster and faster current and more non-uniform current, they can become much more sinuous and eventually produce curved forms that can either be curved outward like this, which we would say was linguoid, or curved inward, curved upstream like this, which we would call lunate. So wave ripples are produced by this sort of oscillatory current, and in this example you can see that those ripples are symmetrical and they're pretty high with respect to their width. And what this produces in wave ripples that's unique is it produces cross-bedding that goes in two different directions, even within the same bed. This is a great example of wave ripples viewed from the side, and you can see here that there are cross beds going in both directions, even within the same layer of sandstone. So here we've got cross beds tilted down to the left. Here we have cross beds tilted down to the right, and that is telling us that the current is switching and going back and forth, and in this trough, sediments being thrown up and then deposited, and then being thrown up that way and deposited that way. Same thing down here. You can see that sediment's being deposited on both sides of those ripples. You can see the same sort of thing in larger scale bed forms like dunes. This is an example of what's called herringbone cross-stratification. You see a surface here where you have cross beds going in one direction above it and going in the other direction below it, which to some geologists back in the day looked kind of like the bones on a fish. Hence the word herringbone cross-stratification. What this indicates is that there was a current going that way, or rather a current going that way first, and then a current going this way first, and a current going that way at some later period of time, and that those currents persisted for quite a while because they're actually in separate beds. And so this is a great indication of tidal currents. Sediment being transported in one direction for a long period of time and then switching directions for a long period of time. One last form of sediment, of cross-stratification that deserves mention are these two, HCS and SCS. These are abbreviations for hummocky cross-stratification and swaley cross-stratification. These are two different forms of the same thing, and essentially HCS and SCS are good indications of long period oscillating flow. In other words, very large waves that produce an oscillation over a fairly long period of time. By fairly long, I mean tens of minutes maybe, or a few minutes. The only difference between them, what storm waves produce on the seafloor is they produce a series of bumps called hummocks. There's 4 of them in this diagram. And those bumps then get draped with sediment to produce these mounds of sediment that look something like this. This is the only form of cross-stratification where the cross strata are actually convex up. So that characteristic convex up curvature is a feature of hummocky cross stratification. So this bed right here was deposited on the seafloor offshore when a storm came in and brought sand from the beach to that offshore region and then reworked it into a series of mounds like this. Swaley cross stratification is basically the same thing, except swaley cross stratification would occur closer towards the beach and under conditions of more erosion and less deposition, so that instead of preserving both the hummocks and the depressions in between them called swales, you just preserve the swales. You no longer have that convex upward cross bedding that you have with HCS, and instead you get an erosional surface with sediment deposited inside that swale. Okay, the last thing that we've got to talk about with respect to depositional sedimentary structures is grain fabrics. There's a couple of them that I want to talk about, but just generally, most sediment can be deposited either in a very well-organized fashion, such as this, where you can see a clear layering to the sediment. It's very well organized, fairly well sorted, versus this bed here, which is completely disorganized. You have large class mixed in with small class, gravel mixed in with mud, etc. And we'd say this is a disorganized fabric. The fabric of a sedimentary deposit can tell you something about how it was deposited. In this case, debris flows typically produce disorganized deposits, whereas water lane deposits, such as streamflow deposits, produce a more ordered fabric. All right. One of the grain fabrics that is very useful in determining something about the conditions of deposition is graded bedding. Graded bedding is a feature that occurs within a single bed that, say this bed right here begins right there and the grain size increases as you go up. That's inverse grading. Bed begins here, the grain size decreases as you go up. That's normal grading. And what graded bedding tells you is it tells you either something about sediment falling out of suspension or sediment being deposited under conditions of dispersive pressure. So in this case, that inverse grading may tell you that this gravel was deposited by a process similar to a grain flow, where you had that dispersive pressure being a mechanism of keeping things in suspension, and the smaller grains were simply filtering through the spaces in between the larger grains, producing that inverse grading. The more common case is normal grading in a deposit. Normal grading simply is size grading produced when sediment falls out of suspension and the larger settles faster than the smaller, producing a graded deposit. So this is telling you that all of this sediment was thrown up into suspension and then settled down, and where it settled or when it got reached the bottom was a function of how large the grains were. Another grain fabric that's important is imbrication, and imbrication is a fabric that's pretty well illustrated by this photograph. This is taken next to a river in New Zealand, and all the grains you can see here are all oriented the same way. They're shingled, and what that's telling you is that the current direction was like that, and the grains here were basically deposited leaning up against the grains in front of them in a way where the current couldn't move them anymore. There are actually, however, two different types of imbrication. The most typical is when sediment rolls on the bed, and when sediment rolls on the bed, we'd say it's carried in traction. The rolling will take place about the long axis. So the long axis is the axis along which that grain will roll, and the B axis, the intermediate axis, is going to be the one that's leaning up against class in front of it. So we would call this A transverse and B, imbricated imbrication. In other words, telling you that the current direction is like that, as shown here. The other type of imbrication, though, that can occur under conditions where grains are suspended. When grains are suspended in a flow, they tend to orient themselves with their long axis parallel to the flow direction, and so you end up getting this long axis being the one that's imbricated. And in that case, we could just call this long axis imbrication. It tells you that the grains were carried in suspension because a grain wouldn't roll such that its long axis was parallel to flow. So here's a great example. What we see in this example is that the long axes of all of these gravel clasts are the ones that are imbricated, and this tells you that these large gravel clasts were actually suspended in the flow and not rolled on the bottom. And this entire package of sediment is one big debris flow that carried these large grains in suspension. Okay, the last type of depositional sedimentary structure that I want to talk about today is called parting lineation. A lot of times, mainly in association with sand beds that are plain laminated, what you see on the upper surface of those plain laminated beds is a pretty clear lineation. You can see lines going in this direction. And those lines are caused by the current stringing along grains parallel to the current direction. And what they essentially tell you is that the current was either going that way or that way, but not that way. So they're a good current indicator, and like I said, they're usually associated with plain lamination. And so here we're looking on the upper surface of a plain laminated sandstone bed. Okay, thanks for listening. In the next video, I will talk to you about erosional structures.